Thanks, Matt, and welcome you all to the Institute of Astronomy. So what I'm going to talk about today is the large-scale structures of the universe. And this is a very hot topic because recently, in 2019, half of the Nobel Prize was given to James Peebles for his work in physical cosmology. And the other half is shared between Michel and Didier, Professor Didier, who is at University of Cambridge, right next in the next building. They have given this prize because they have done a discovery in the exoplanet or so. So I'll talk mostly about the large-scale structures, but I will mention why the large-scale structure is actually important. The exoplanet, on the other hand, is on the very small-scale structure kind of thing. It's on a very small scale. I'll first of all define what do you mean by scales and so on. So the brief outline of my talk would be, first of all, I'll discuss what is astrophysical scales, what are the different scales that we have in the universe. And in the next part, I will talk about what structures exist on those astrophysical scales. Then I'll define what do I mean by large-scale structure. And then I'll talk about how we can understand the formation of these large-scale structure from the Big Bang perspective. And in the final thing, I'll just give some future prospects of this field and where we are heading to. So let me first of all start with astrophysical scales. So when we say about astrophysical scales, the most basic scale that we can think of in terms of distance is the size of Earth. So Earth, if you take, for example, has a radius of something like 6,000 kilometers. But average distance between Sun and Earth is like 150 million kilometers. So we cannot use always the kilometer as a distance scale to measure the astronomical distances. So what we usually do is we express this in terms of how much time it takes for light to travel that much distance. For example, the average distance between the Sun and Earth in this system would be like 8 minutes, 8.25 light minutes. That means it would take 8.25 light minutes to cover the distance between the Earth and Sun. So if you take that unit, the distance between the farthest dwarf planet, so to speak, is Pluto, and Sun is around 5.5 light hours. So when we talk about scales in the planetary systems, we talk about the scales of the order of few light hours or so. Okay? Pluto is not at the edge of the solar system. The extent of the solar system is much more. It's like 16 light hours in that unit. So NASA has sent a probe called Voyager 1, which was launched in September 5, 1977, which just recently entered into what is called as interstellar space. So it has left the extent of the solar system and it has gone now to the interstellar space. Interstellar because now it's no more the solar system, it's this space between the different stars that we are talking about. So if you take that, when we talk about which is the nearest star to our solar system, or for example Sun, that is a Proxima Centauri. And this Proxima Centauri is around 4.25 light years away from the Sun. So that means when we talk about the distances in interstellar space, then we resort to units of light years. When we talk about the scales in solar system, we talk about light hours. Okay? If you look at Milky Way, for example, if you go to a countryside away from the city light or something, you see a very hazy band of lights like this or over here. And you see a very large number of stars which cannot be individually distinguished by the naked eyes. So, and this is what is called as Milky Way. So it is very important to note that no man-made object has gone outside the Milky Way and taken any pretty pictures. So whatever I'm going to show you are actually not the real pictures of Milky Way. So I just used my imagination how the Milky Way would look like, and I came up with this best picture of Milky Way that I can get of. And this is like this. So if you want to go from one edge of the Milky Way to another edge of the Milky Way, it would take something around 0.125 million light years. Now we are talking in terms of millions of light years rather than just light years. Okay? If you take that yardstick, the solar system is not actually at the center of the Milky Way. It's actually very far away from the galactic, what is called galactic center. It's like 26,000 light years away from the galactic center. Now this was a pretty boring picture of Milky Way. A more realistic one would be something like this. This is again not a Milky Way, this is some other spiral galaxy, but we can see that it's very similar in structure with the Milky Way. So as you can see, this is a spiral structure of the galaxy, and there are around 200 to 400 billion stars in this galaxy, and there are at least 100 million planets in our own Milky Way. So if you take that yardstick, this is a galactic center, and the solar system would lie somewhere over here, which is much far away from the galactic center. Okay, so when we say about any galaxy or something, galactic scales or something, we talk about in terms of few millions of light years, not just light years. Okay, so our galaxy Milky Way is not the only galaxy in the universe. There are various other type of galaxies. I'll just show you two examples which are very famous and very nearby. That's why you see very beautiful pictures. This is one of the galaxies in the Andromeda constellation. So here is the Andromeda constellation, and there is a galaxy called M31. M because it's a Messier catalog. We catalog the galaxies in different database that's called Messier or something. This is an M31 galaxy in Andromeda constellation. Why this galaxy is important? Because this is the largest nearby spiral galaxy, which looks very similar to Earth. So if you look with your 2-inch telescope, the galaxy would look something like this. So don't expect to see like this. This is taken from a very big telescope, like 2 meter, 5 meter class telescope. So to just give you an idea about what is the diameter of this M31, if you want to go from here to here, for example, in this Andromeda galaxy, it will take something like 0.22 million light years, which is like roughly 2 times the size of the Milky Way. So it's much bigger than the Milky Way. In the same constellation, there is another galaxy in this triangular region. It's called M33 triangular. This galaxy is actually smaller as compared to both Andromeda as well as the Milky Way. This galaxy has a diameter of something like 0.03 million, so it's very small as compared to the other one. So this is an artist impression. So this is not a real picture. This is an artist impression how the group of galaxies would look like in the nearby universe, in the very local, what we say. So there are not just 3 galaxies. These 3 are major in diameter or in sizes. There are various smaller galaxies as well. This is called LMC, which is called Large Magellanic Cloud. Small Magellanic Cloud, NGC, some dwarf galaxies, we call them dwarf galaxies. So a local group consists of something like 30 galaxies or so. So when we talk about intergalactic space, then we talk about the distances between the galaxies. So it's no more the galactic scales, but it's an intergalactic scale. So the intergalactic scales, the distance that we talk, so the Milky Way and Andromeda galaxies are separated by 2.5 million light years, and similar with the triangular galaxies. So when we say intergalactic scale, we mean more than 3 million light years or so. So typical scale of the galaxy is like 0.1 billion light years. Intergalactic scales are like 3 million light years and above. So this is what we see so far. So there are 4 scales that I described. The first one is a planetary scales, which happens on the scales of like 100 light hours or so. Then there is interstellar, that means the distance between different types of stars, which is of the order of something like light years or so. Then I talked about the galactic scale, the galaxies on which it exists. It's like 0.1 million or 0.5 million light years. And when we talk about the distances between the galaxies, which is intergalactic scale, which is like 2 million light years and above. Okay? So on all these scales, there exists a structure. There exists some pattern. And this is what I'm going to discuss. First of all, I'll define what do I mean by structures, and then I'll discuss what are the examples of the structures that we see on these different scales. So the structure, when we say a structure in the universe, what we mean is a gravitationally bound system. For example, if you have an Earth and Moon, the Moon cannot leave Earth and go away from the Earth unless a force acts on it. So that means the Moon is bound to Earth. So that is a gravitationally bound system. The more technical way of saying is that there is total energy is negative, so they are bound together. But there exists a structure on all scales. So I just describe what structures exist on these 4 different scales. So if you take a look at planetary scale, there are planetary solar systems like our own solar system. For example, this is an example of a Kepler-62 system, where there exists a very cool star like Sun, but which is slightly cooler, and there exists 5 planets. And you can see that the size of this one is very similar to solar system, slightly less than this one. So when we talk about planetary scale, we talk about the scales of light hours, and many planetary systems exist on those scales. When we talk about interstellar scale, what we see is the stars are not actually distributed randomly in the universe. They are also clustered on some scales. This is a famous example of a Pleiades cluster, which you can see as the 7 sisters in this cluster. And the extent of this cluster is around hundreds of light years or so. And I explained that there are galaxies, but our Milky Way is just one type of galaxy, which is a spiral galaxy. We have seen many different types of galaxies, and all of these galaxies are gravitationally bound, so we can call them as a structure. For example, we have seen a bar kind of galaxy, which is a Huygens bar, which is an irregular galaxy, no shape actually, and this particular galaxy also has no definite shape. Elliptical galaxy is more like elliptical in nature, so that's why we have elliptical. Spiral is like a Milky Way kind of, or Andromeda kind of example, and then there are lenticular kind of galaxies also. So all these galaxies have a scale, something like a 0.1 million light years or so. When we talk about intergalactic scale, very large scale, we see that galaxies are also clustered. For example, I mentioned that there is a local group of galaxies. This local group of galaxies is over here, very small region. This is a Virgo cluster, a very big supercluster, which is very near to our local group. So galaxies are also clustered on some scales, and they are also somewhat gravitationally bound systems. So for each of these scales, like planetary scale, interstellar scale, galactic scale, or intergalactic scale, there exists structure. And this is the structures that exist for each of these scales. Now, when we say a large-scale structure, whenever we say a large-scale structure, what we mean is a scale above the galaxy cluster and above. That means we always talk about 3 million light years and above. I will not talk about the planetary scale. That is also very interesting, but for this talk, I will talk about only the scales above the galaxy clusters and so on. So this is what I am going to talk about in the next part of my talk, which is a large-scale structure. So when we want to see a very large-scale structure, we need to find out galaxies in the universe. And the best way to find out the galaxy is using a very big telescope. So we have something like a Sloan Foundation 2.5 meter telescope at Apache Point Observatory. And it has collected data over the many years, okay? And it has found out many different kind of galaxies. For example, we collect all these galaxies in a survey called SDSS survey, Sloan Digital Sky Survey. And we have a sample of different galaxies detected in this sample. For example, here are some spiral galaxies, here are some dwarf galaxies. I mean, various kind of examples from the SDSS sample. Now, the number of galaxies that has been detected in this by this whole telescope is something like 200 million or so. So we cannot actually study each and every galaxy. If we try to do that, it will take more than age of the universe to just study all of them. So instead of that, what we ask this question is, how are these galaxies actually distributed in the universe? That can give us a clue about how do they form, why they have a structure like spiral galaxies, some elliptical galaxies, and so on and so forth. To do that, first of all, we need to understand that we need to locate a galaxy in the sky. And there are 3 numbers required. Whenever we want to detect any galaxy, we need to define 3 numbers. The first number is the longitude, how much is it with respect to the horizontal axis, how much is it the latitude in the vertical direction, and the third one is the how much is the distance. So this is a spherical coordinate system that we are talking about. So showing a 3-dimensional map of a galaxy is a very convenient, but it's actually not very useful to visualize the thing. So what we usually do is we combine this longitude and latitude in one coordinate. It's called direction. We just project them onto a plane, and it would look something like this. So you will always see a plot called a survey of galaxies, which is shown something like here. So this represents direction, which combines the information of both longitude as well as latitude. And this, from this point onwards, this is the distance of a galaxy. So for example, if I have a galaxy somewhere here, it is at a distance of something like 200 megaparsec. A megaparsec is just nothing but 3.26 million light years, so I just switched the unit. And you can see the light, the galaxy would be here, and it is at a direction from 0, wherever you start. The galaxy over here would be at slightly different, in the different direction, and it will be at slightly higher distance as compared to the Earth. Okay, so this is how we see the large-scale structure, and this is a very important part because I will show the different plots from the observations in the movie. So this is the observation of SDSS galaxy that I mentioned, 208 million galaxies and so on. Each dot over here is a galaxy in the SDSS sample. The best thing that, and the most important thing that we want to understand over here is that you see that the galaxies in some regions, such as here, are more clustered. They are more together. They are assembled together. This is called galaxy clustering. Okay, and in some regions you do not see much of the light. So there is a void, which is called void or something. So if you look at our theoretical prediction simulation, for example, they predict something like this. Each dot over here is a galaxy, but you do not see any clustering over here in this case. The question is why there is a clustering of galaxies in observed universe, whereas our theoretical prediction does not do anything about this. And to understand that, first of all, we need to understand how do the galaxies form at first place. And this all starts with the Big Bang. So now I will talk about how did this large-scale structure form from the Big Bang. So in the beginning, we know that the universe was very small. And it was not only small, when it was created, it created a lot of elementary particles and also very high energy radiation. Okay, the first particle that was created was like electrons, which are negatively charged particles. Okay, then there were protons, which are positively charged particles, and there was also very high energy radiation, which I will call it a photon, which is a very, very high energy radiation. Now, we know from very basic understanding of our electrostatics that whenever we have a proton with a positive charge and an electron with a negative charge, they have an attraction towards each other. This is called Coulomb's attraction. This we learn from the electrostatics, force of electrostatic and so on. So when they combine, when a proton captures an electron, the electron orbits around it, and it is what is we call as a hydrogen atom. Okay, so this is a hydrogen atom, a very basic hydrogen atom. So in the universe, all the protons will attract electrons and produce a hydrogen atom. However, there is a problem. The problem is there is a high energy radiation present, very high energetic photons. What happens is these photons actually collides with this electron, and then they ionize. They just ionize and make them separate once again. And this was very crucial in the early stages of the universe. For example, in the early stages of the universe, protons and electrons were separated. They were not able to combine together to form hydrogen. It's because of the very high energy radiation that was present in the universe at that time. But we all also know from the Big Bang theory that the universe was expanding. Okay? So if there is an expansion of the universe, what would happen? If there is an expansion, more space would be available now for the different particles, for example, these elementary particles and high energy radiation, to occupy this extra space created by this expansion of the universe. But we also know that radiation is traveling at a speed of light. Okay, so it's the speed of light. As a result, what happens is these high energy photons occupy the extra space available due to expansion very quickly, as compared to the elementary particles, which are also traveling very close to the speed of light, but slightly less because they are heavy particles. So technically speaking, what it means is that you have a less number density of the photons, and it drops very quickly. As a result, what happens now for hydrogen, electrons and protons are combined together to form hydrogen. But now it can also ionize by the radiation, but the radiation has diluted because it has occupied extra space. Okay, so as a result, you form hydrogen atom. And this radiation field that you see over here now do not interact with hydrogen. It just travels through the space, and we can see these photons. And we all have seen these photons. For example, when you watch a signal like this TV signal like this from in your old television set, this is a 1%. This is a static noise from the television, and 1% of this static noise is actually contributed by this what are called cosmic microwave background. Okay, and this signal we have seen this signal also in using satellites. For example, we have 3 satellites. One was COBIN in 1992, WMAP in 2003, and Planck in 2013. And in all of them, we detect these signatures of this cosmic microwave background. So this is when there was a separation between the of the electrons and protons. I mean, when there was a recombination of electrons and protons. This was very important discovery because this ruled out the other competing theories of universe, which was like steady state theory. And 2 of the Nobel Prizes were given just for this. One was for the discovery of CMB in 1978, and in 2006 to measure the properties from these maps, how it looks like. So there is a complicated physics going on in the cosmic microwave background. Okay, so here we were. So these photons, actually we can see them. But what happens to the hydrogen atom? I won't discuss anything about the hydrogen atom. So what happens due to the hydrogen atom is that they start to come close together under the force of gravity. Okay? Because now there is a gravitational force acting on the hydrogen atom. So they form a very large clouds of hydrogen atoms in the universe, and we start to form what are called structures due to the gravitational collapse. So there is a collapse going on now. So this is what is known as the hierarchical structure formation. So first stars are formed in galaxies, then galaxy clusters. This is called hierarchical structure formation. And you can see over here there are 3 different structures where the gas is getting accreted. Why we consider why we so much concerned about hydrogen is because hydrogen is the most basic element in the periodic table. And the second thing is hydrogen is the most basic fuel for any star formation. Okay, and also it's important to note that whenever there was gravitational collapse happening, there was also universe was continuing to expand. So all the time universe is continuing to expand, and so on. So that was all right. That I just gave you a feeling of how it works. But do we actually do it when we do it on the computers or not? So this is a cosmological simulation performed on a very supercomputer, very high supercomputer. This is a universe when it was very young, which was like uniformly distributed. So there was electrons and protons. Nothing was able to form hydrogen atom. This is how it looks like when it evolves. So here you start to see some more collapse of the gas due to gravitational collapse. You see more structures over here. You see more structure, more structure, more structure, and this is a present day. This is more structures. It's more clustered together. So the galaxies are more. So each dot over here is a galaxy. So the mass is like galaxy. So they form in clustered region because of the gravitational collapse. That's what we think today. So till now, what I have presented is something like this. So I told you about this different scales, and there exists a scale on different scales, structures on different scales. I talked about there exists a galaxy clustering from the observed data, and I explained them how it works. It's start with the Big Bang. During the Big Bang, we cannot. The hydrogen atom was not able to form because of the high energy radiation, but because of the expansion, we start to form hydrogen. And then when this hydrogen is formed, then due to the gravity, it starts to collapse, and then we form structures like this over here. So this is all right, but why these large-scale structures are so important actually? And this is what I'm going to talk about in the next maybe 5-10 minutes or so, which is future prospects. What we can learn from these large-scale structures, the galaxies that we see, so many galaxies. So we know that the composition of the universe, I talked about the universe is expanding, but I never explained why it is expanding. And one of the reasons that we think today is the dark energy that is responsible for the expansion of the universe. And this constitutes around 70% of the universe. And also I did not mention about how the hydrogen atom is actually collapsing in the gravitational potential. We think that the gravitational potential for this very earliest type of structure is set up by what are called dark matter. which does not interact with ordinary matter. So we all are made of baryons, which is called ordinary matter. The dark matter is something we don't know about for this for sure. So whenever we see a galaxy or something, it's just coming from this 4.6% of the baryonic component. So this baryon, the ordinary matter, is like 4.6%, whereas dark matter is like 24%. It's huge. So how can we use this information about the large scale structure, this 4%, to understand about the 24%, like dark matter or so? And that's what we want to know. To do this, I'll give you an example. This is a distribution of light, and the question is, what does it corresponds to? Some of you may think that this corresponds to star cluster. Some of you may think this corresponds to galaxy cluster, but it is neither of them. In order to know what it corresponds to, we need to see the faint objects. Okay, so to gain the more important about this one, we see the fainter and fainter objects. When we see, we can do this by either increasing observation time or by using a very big telescope to see a very faint object. And when we see a very much fainter objects, what we see is this does not correspond to any galaxy cluster or star cluster. It corresponds to a distribution of light coming from major cities in the night. So for example, London is over here somewhere. Okay, Moscow is here, Delhi is here, and Beijing is somewhere here. So this situation actually that I explained is very similar in the universe. For example, we know that the surface of the Earth contains 70% of the water, which does not emit any light because there is no one living there. 30% is land. Okay? So think of water as a dark energy, which is 70%, which is not emitting anything. Think of land as a total matter, dark matter plus baryons. But only major cities like on Earth emit light. This corresponds to galaxies, something like 4% they emit. Okay? And we know that major cities on Earth is also the locations where there is a large number of people living. For example, London contains more population as compared to Cambridge. So major cities corresponds to large population density. In a similar way, galaxies corresponds to a large matter density, which is called a matter density. So only when we see a fainter light from small cities from here, we realize that the light distribution corresponds to Europe and Asia. So similarly, when we see fainter galaxies, then only we can trace the dark matter distribution in the universe. So this is one of the applications of the large scale structures. We need to detect very faint galaxies. And there are also other implications of this for galaxy formation and evolution. So how do the galaxies form? How do they interact with the environment? This is something we can learn only by using this large scale structure phenomenon. I did not mention anything about what happens between the galaxies. There is a medium between galaxies. It's not empty. There is a lot of material in the intergalactic space. That's called intergalactic medium, which is actually a current very hot topic in area of research. Okay? So this information, all this large scale structure was possible because James Peebles has laid down the framework on how to do this analysis. How to measure the galaxy clustering and so on and so forth. That's why he has been given half of the Nobel Prize. And at the same time, this is not just a complete story. We also know there is a small scale structure on a very small scales, like exoplanet. So Nobel Committee has tried to compromise between a very low, small scale and very large scale. These are not different. They are just a complementary probe to tell the story about our own universe. Thank you very much.